Chapter 4, Section 8, dividing a monomial and dividing a binomial, or a two-term polynomial. Well, the first one we're going to look at is dividing monomials to really should be just a review of some things that we should know about division and fractions. And this is probably when I'm going through the first few chapters of this book, I really emphasize the understanding how fractions work a lot, because if you're a little weak in some of the fraction areas, it will bite you a little bit during this. So this is time to remember exactly what's going on with fractions and stuff. So, well, let's look at what the book has to say about this. It says, first consider division by a monomial. It says when dividing a monomial by a monomial, we subtract the exponents when the bases are the same. That's basically the rules of powers. So they got that rule that they're reminding us of. And I don't know if this is a good caution or not. The reality is that we do the same thing with constants too. If the constants have same bases, if I factor 42, I really get 3 times 14, and so I have 3 over a negative 3, where I can subtract those bases or exponents because the base is the same or close to the same after I factor out a negative 1, and I get 3 to the 0 power. I get a 1. Basically anything to the 0 power is 1. And so they go through this. We have a like base here too of a to the second power, and this is really a to the 1 power, so we subtract exponents, so we get a to the 2 minus 1, and the b is like bases here again. Remember, these are all multiplications, so we can break out this fraction basically any way I want. In reality is what they're doing is they're taking 42 over negative 3 as a separate fraction. You get negative 14. You take the fraction a squared over a, and that'll give you this shortcut, and then times this fraction b to the 5th over b to the 2nd, which will give you this shortcut. That's why we can apply that rule of subtracting exponents for division. This is good review. This is really a review of a couple sections in chapter 1, and they're going to do this. Not necessarily that we don't, especially if you have a calculator, you're probably never going to think about doing it this way. The reason they're showing this is to remind us exactly how fractions work, especially with addition and subtraction. It says to divide a polynomial by a monomial, we'll note that since a over c plus b over c is the same as a plus b over c, or if I want to say that in words, if I have the same denominator when I'm adding fractions, I just add the numerators, right? Well, it goes the other way too. So if I have an addition over a denominator, I can break that out into 2 fractions that are added together. So a plus b all over c equals a over c plus b over c. So, you know, this rule about adding, we do it this way. We go through all this manipulation of fractions to get a common denominator and so on so we can add. Well, when I have a fraction this way, I can break that into an addition of 2 fractions with a common denominator, right? So like if I had something like 86 divided by 2, like I said, you would basically probably take out your calculator, or you could probably do this in your head, thinking of long division, which we'll be reminded of here in a bit too, and get the answer 43. But they want to remind us that say, hey, let's look at how this works in terms of these fractions. I could write 86 in its standard form, is what it's called, is basically writing the 8 means 8 tens or 80, and the 6 means 6 ones. So I'd say this is 80 plus 6 all over 2, which I can break it into 2 fractions, 80 over 2 plus 6 over 2. So in this case I'd get 40 or this makes 4 tens or 40, and this makes 3 ones. So I get 40 plus 3, which is 43. Now, they're just showing us to show us and remind us of what happens when we add fractions and so on. Because when we get variables mixed into this thing like this, we need to remember that I can break this into two fractions or basically apply this monomial divided by a monomial, a single term divided by a single term. So like in this case, I can break this into two fractions added together with this common denominator of 2x cubed. So this is 80x to the fifth over 2x cubed plus 6x to the seventh, that second part of the addition, over this common denominator of 2x cubed. Then I can basically follow the rules we just went through. I can simplify each one of these fractions. I can do the division of the constants, which is going to be 40, and subtract the exponents. I get x to the 2 power. 6 divided by 2 is 3, and x to the 7th over x to the 3rd is x to the 4th. I should be able to. And practice this again. When we're working on these things, you could go maybe some other ways that you may have found some shortcuts to try to deal with exponents. Apply the rules as given, because it's going to be important. At the very least, it's how the book explains it. So if you got a little confusion on a problem, you can go back to it and say, yeah, okay, I get that part. So they're just applying rules that we've gone through already in this course, or the prior course of this too. So when they give it in terms like this, if they say divide, remember division is just a fraction. And then we go back to fractions, where we spent most probably your math career trying to avoid fractions and trying to do divisions with calculators. Well, here we have division. It's going to serve you to think of it as a fraction now. And when I write this as a fraction of x to the 4th plus 15x cubed minus 6x squared all over 3x, that is the same as this divided by that. Then I can break that out into 3 different fractions that are added together, and then I can apply the rules that we just talked about. Okay? If there's any questions on this, how to think about having a common denominator and breaking an addition in a numerator over a single denominator into multiple fractions, it would be a very good time to do an Ask My Instructor, or give me a call during my office hour, and we can talk about that, or make an appointment and we can get together and we'll talk about it. So they do this. The other thing too is, remember that fractions, if I don't have a constant up here, there really is a 1. So this is 1 times x to the 4th over 3 times x. So I could have 1/3 times x to the 4 minus 1 power, which is to the 3rd. Okay? A lot of stuff kind of hidden right in here. Review of all the different things and ways that we can show fractions. And then checking. So if we figure out that this is the result of my division, right? I divided by 3x, right? Well, I should be able to take my result and multiply it by 3x, my divisor, and check to see if I get the same original polynomial. And that's what they're showing here. Well, take 3x times my quotient, the result of this division. Take it times the divisor and see if you get the original polynomial. If you don't, then there's a math error, or you got some kind of concept error around fractions. So here's another one showing division. So you probably, if in just math, you've probably never imagined you would take divisions and then treat those as fractions. But in the case of algebra, you really need to. So here's a division by a monomial. Again, we can break this out into separate fractions that are added together. And careful of your signs. especially here. I usually like to try to change everything to an addition because I see a lot of errors around when I'm subtracting a negative number. Okay. And then the check process. And I would say definitely these do take a little bit longer, but it takes a lot of work in some of these cases for these problems. I'd hate to do a lot of work and then find out I did it wrong, which a lot of times could be just a little sign error. If you check these, you'll probably catch sign errors. And sign errors are not, I said little thing, really are not little things. Sign errors are a big deal. So make sure you check. Now we're going to get into something too, the reminding of some things we've kind of avoided since we got calculators too, is long division. So dividing by a binomial, this is another strategy to deal with this. I think breaking into fractions is a best strategy, but we can use some other things too. And strategic things are work, like I said, if we had a monomial. Well, in this case, we're going to divide by a binomial, a two-term thing. And breaking this down into separate fractions probably isn't going to simplify anything. If I put this as x squared over x plus 3 plus 5x over x plus 3 and 6 over x plus 3, really nothing simplifies very easily when I do that. So they're going to show us long division. If we divide, and I wish they would go through one with numbers here in the book, but if you think about that, when you do long division, you basically start with what you're dividing, you're checking the first number in the place right here and see if it goes into that. Well, this process is the same thing. So they go in here and say, well, x plus 3, what I do is I check the first term against this first term, and I'm going like, what would I need to multiply by to get x to be x squared? Or another way, if I divided x squared by x, what would I get? X, okay? Well, there's my first part of my quotient, the answer to my division. Well, what do we do in long division? We take that and then we multiply it by our divisor, we put it under here, and then we subtract. And it comes from the fact that division is really multiple subtractions, right? Multiplication is multiple additions. Division is multiple subtractions. So they multiply x times each term. Make sure you use the distributive property. So x times x is x squared. X times 3 is 3x. Now we're going to subtract that, which means take the opposite of the entire thing. And the key is that if I do this correctly, when I put these things together, I add like terms in a sense, is this first term, or this x squared term, will go away. I end up with 0x squared, or 0. So then I do this other subtraction, which is going to be, again, this is a negative 3x. Added to 5x, I get 2x. So now I got a new thing that I'm dividing into, and I drop the next part, or next term of this polynomial. So I put the plus 6 down, and then I basically start over my division process. I look at the first term, this x plus 3, the divisor. I look at how many times will it go into this new thing. It's like a completely new division we're going to go through. And hey, that goes in there 2 times. So I put 2 up there, I multiply back, and I end up with 2x plus 6. I subtract, I get 0. And basically I'm done. Okay. Now, real key part of this is to check. Very easy to make some errors in this process, especially when you're first starting this. But I can check. I can take my quotient here, x plus 2, and take it times the divisor, x plus 3, and I should get this polynomial back. And that's what they do next here, is they check that. And they also talk about one other thing here. I kind of skipped to that. They don't show the check either, but if you think about how division works, like if I take 5 divided by 2, and I do that this way, I would go, 2 goes into 5, 2 times, right? And then I multiply back, I get 4. And I subtract that from 5, I get a 1 left over. I got a remainder of 1. And what does that remainder really mean? It means that it is 1 part of that divisor, or 1 over that divisor. So I could say that 5 halves is the same as 2 plus the remainder of 1, or what that really means is 2 plus 1 over 2, which is what I was dividing by, right? Or 2 and 1/2. So in this case the remainder was 0, and so on. And we're going to find better ways to do that division here next chapter, but when we have remainder 0 things or factor things, we can find a better way to do that. But they're trying to remind us here that, hey, there's just a remainder of 0, and what that means is you have this times this plus whatever that remainder is, and that adds together to be my dividend, my original polynomial. Well, let's look at example 2 here, because this one we actually get a remainder, and we have to deal with the remainder. So they go through the process again of, we look at the first term, and we have 2x squared in the dividend here. We want to know how many times does 2x go into 2x squared. Well, it'd be x, because x times 2x is 2x squared. Well, I multiply back, distribute over the divisor, and I get 2x squared minus x, and I'm going to subtract that. The key to know that if I did this correctly is that first term of my original will drop out. It'll go to 0. Then I subtract 5x minus x, minus a negative x, which is 5x plus x is 6x. I drop down the next term, which is, so I have this new dividend really. I'm going to divide 2x minus 1 into 6x minus 1. So I check the first terms against each other, and 2x will go into or divide into 6x 3 times. So I take 3 times 2x and I get 6x, and 3 times negative 1 is negative 3. So I end up with subtracting this, and the 6x goes away to 0, or goes to 0, which means I got the right numbers in here. And then I have negative 1 plus 3, and I get a positive 2. Well, I don't have any other terms to drop here to make a new polynomial to divide into, so this is my remainder of 2. And we could answer it that way, and we'd say x plus 3 with a remainder of 2. Well, that doesn't work very well in algebra, because the remainder assumes that you know what the divisor is. And the way to express that is to take the remainder and put it over the divisor. So I'd have x plus 3 plus this remainder 2 over what I was dividing by, this 2x minus 1. So that would be the quotient. The result of that division is this addition, or this complex fraction is there. Okay? And how would we check that? Well, you take the quotient times the divisor, which the divisor again is 2x minus 1. That's where they get 2x minus 1 plus times, x plus 3. Multiply that, I'd use FOIL, and then add 2, and I should get the original dividend, or original polynomial. And again, I would make sure you check to make sure you haven't made an error. And there's a lot of subtraction. There's subtractions of negatives, a lot of pretty common opportunities for errors. So that's long division applied to algebraic expressions. Now they give us some other examples here, and with a reason. They're not saying, oh, here, look at some more of these, but they're usually coming up with some new types of things that you're going to run into. Well, like in this case, x cubed plus 1 divided by x plus 1, I run into some things here when I put the dividend in. I don't have terms to match up when I'm doing the subtraction. So I can always fill in the terms. And I think this is probably one place where, when we talk about a degree of a polynomial and the degree of the actual terms and those types of things is useful, is I can represent every degree of this polynomial by putting 0 times it. And that fills in the places for this kind of thing. There's a big difference when we're trying to make sure our places are set up for dividing numbers. This is the same situation. So in this case, we put this in here. This is probably where you want to start, and you say, hey, I'm missing the x squared term and the x to the 1 power term. This is really x to the 0 power degree 0. So let's fill them in. And I can always do that because of this law of 0. If I multiply by 0, it's 0. It doesn't matter what I'm multiplying by. Well, we fill them in specifically with a strategy to deal with this long division. So we got x squared. We compare this. How many times is x going to x cubed? And that'd be x squared. I multiply x squared times these. I get x cubed plus x squared. And I'm subtracting that. Well, I need something to subtract it from, so we have this 0x squared in here. And when I got 0x squared minus x squared, I get a negative x squared. I drop the next term, which is 0x. This gets really tough if you forget to fill in these 0 terms here. Okay. Well, now this is my new dividend. I look at the first term, what do I need to multiply by to get this equal to negative x squared, which is a negative x. Multiply back, subtract, now I have a term to subtract from, and so on. So we have this new dividend. In this case, we end up is 1, and I multiply and subtract to get a remainder of 0. So with that check, basically I'd say plus 0 for remainder right here at the end. To check this, I take the divisor times the quotient. I should get that dividend. Okay. And when you look at this, I have to distribute x times x squared, x times a negative x times 1 times these, right? And that's how they're showing this filled out. Combine like terms, and I got negative x squared and positive x squared is 0, x and negative x is 0. I end up with x cubed plus 1. In fact, they're going to actually use this as a pattern that we're going to go through at some point of dealing with these kinds of things, x something cubed plus something cubed. There's actually a pattern to factor those and so on. Just a little note going into next chapter. Remember I was talking about degree. It is good to rewrite things in descending order. Like this one here, here's the original. It's got 9a squared plus a cubed minus 5. Writing things in descending degree order is essential for this long division to work correctly. So what they do here is say, hey, this is degree 3 and this is degree 2. We should put that in front. So they change the order of that, which is possible because of the commutative property. And then they fill in a 0 for the term that's not represented. I got a 3rd degree, 2nd degree, but I didn't have a 1st degree, and I have a 0 degree. Okay. So they take this and go through the division process. Now notice in this case, which is a nice example to look at, in this case I don't get a like term for this 9a squared. So what do? They basically, you say there's a 0 there, and you subtract 0, you end up with 9a squared. So a times a squared is a cubed. A times a negative 1 is a negative a. There's no a squared term. So I line up, make sure when I subtract, I want to line up like terms, and then I subtract. Well, this goes to 0. That's our goal, right? To get one of the terms of the original polynomial or dividend to go away, right? That first or highest degree term. And I end up with this new polynomial to divide this into. Now I got 9a squared plus a. Remember that we're subtracting a negative a. A lot of sign errors there, be careful. And then I drop the next term of minus 5 or negative 5. So I take then my next question is 9a squared divided by a squared is 9. So I put a 9 there, I multiply back, right? And I get 9 times a squared is 9a squared. 9 times a negative 1 is a negative 9. Notice I got a blank for the degree 1 now. And so I end up with this new subtraction. Remember that this goes to 0. We're trying to get rid of the highest degree term of this polynomial. I subtract, I get a and positive 4, a plus 4. So what this means is I've used up all the terms in the original dividend, so I'm done. This is my remainder right here, a plus 4. So the answer is a plus 9 plus the fraction a plus 4 over a squared minus 1. That's my dividend. There's the denominator. Well, I can check this now. I can take this, multiply them together, and then add my remainder. And I should get the original polynomial. So dividing, long division is an important tool for simplifying or doing division within some of these types of polynomials.